Leave it there. Here's the attendance. Okay, let's get started. I need to log in. Okay. Okay, let's start. How's everyone? Okay? Okay, as I said, if you missed the class on Tuesday and didn't get the exams back, they are lying here on the table. So make sure you pick it on your way out. All right, so today we're going to cover 5.5 and 5.6. They are kind of related, right? We won't be able to cover 5.7, which we'll do next week, and that will be the end of this chapter, right? Okay, so what we have been doing so far is always take an LP problem that's already solved, and you go back and you see that if I make a change here and there, how does it affect the solution? How does it change the solution, right? So we have looked at changing various things, changing the objective function coefficient, and to see how that makes a change. And we also saw by adding a new variable, how does it affect? Okay, so today we'll be looking at one more type. That is, I will change the constant term, change the B vector. Okay, so the constant term, and that means the column on the right-hand side of your constraint. Okay. I would like to take the same example as we had last time, and we just talk through the example with observations. So let me put up this example. This is the same one we had for a while ago. So this example 5.3.1. Okay, so I will put it in the tabular form, so we should all be able to read what that means. All right? So let me put it up. I will need to make changes and okay, so let me put these numbers. You should have this in your note. It's in the book also. Okay. 11. Okay, so that's the initial tableau. We call it I. And then you do your pivoting, and then you reach the final form. That's what I'm writing down here, is the final form. So this can be easily solved, and you will have x4, x2 as your basic variable. I'll have these. It's okay. For this, 2, 0, 5, 1, 2, -1, 6, 11, 1. Okay, that's the example we had for our discussion. We used it a couple times. So today we will have a discussion based on this, and we'll make general comments about how, if I make a change on the right-hand side B, how would that affect the solution, all right? Maybe I'll leave some space here. I will need to mark the right-hand side B is where I will make change. I will change here. Okay. So let's make some observations before we jump in. Okay. Now let's say I make some change on the right-hand side, 28, 50, that I change to some different numbers. And if I carry out the same pivoting process as I did to obtain the final form from here, how will this change cause the changes in the final tablet? Let me rephrase my question. So, do you think this A part will be affected if I carry out the same pivoting process? Will any of this A be changed? What do you do when you pivot? When you say I pivot here, you multiply this by some number and add it on top, right? So the change here will affect the same column, and then the change here will affect this column. It will never come to the left-hand side of the equation. Do we agree? So this will not be changed, and also this left-hand side, the objective function, will not be changed. Okay, so that's important. So let's put it up. Change in B, changes in B do not affect the, let's call, can I call it the left-hand side of the equation, right? Everything on the left. Okay, and then let's look at how the z, the minimum of the z, is computed. We have this formula which we proved. So z0 minus c of the b, and b inverse times b. And then you know this guy here actually gives me in the end b star. That's this right-hand side here. That will be the b star vector. So you see, if I make a change in b, I will change the b star, which is here. And cb will not be changed. The b inverse will not be changed. But then this number is changed, and the z min is changed, right? And then I have to be careful, because if I change, you see, if I change b, b star will be changed. So if I mess up these numbers, these two numbers will be different, then I'm in risk of making them negative. If any of this shall be negative, then the basic solution is not feasible, and then I cannot discuss anything. Is that right? So I need to be careful with that. So I need to make sure that the change I make in B will not make the B star negative. Otherwise, I have to do something else. Need to verify that B star is all bigger than 0. And if that fails, if you made too big a change or some bad change, so let's say some element becomes negative, and then I need to do some new stuff, which we'll talk about today also. Okay, so with that discussion in mind, and let's take a look at this example, and let's say I want to make some change. Okay, so say what changes would I make. Let's say I change the second number, B2, which is originally 50. I will change that to B2 equals 53. That was my number. Okay, so step 1, I need to compute the B star and to check if it's non-negative, right? So let's compute. Then I need to compute the B star. What is the B star? B star is B inverse times the B. So the inverse matrix B we have done earlier. That will be 4, 7, and 1, 2, and you take the inverse of that. This matrix we actually have, that's 2, -1, -7, and 4. Multiply with the B now. So what did I change? I changed this into 53. Is that right? And I want to see what change this is causing in my answer. So now my right-hand side vector will be 28, 53. Is that clear? And this product will give you the new numbers over here, right? We proved that formula, okay? So if you carry out this computation, you will get 316. So this change by there give you a new number here, 3 here and 16 here. And then I see that nobody is negative here, so everything's fine. I will have a basic solution which will be feasible and which will be optimal. Is that right? Because all the coefficients of the objective functions non-negative. Okay? So I would say that the basic solution, what would the basic solution be now? I will have x4 is 3, x2 is 16. So I have 0, 16, and 0, and 3, and 0, 0. Okay, and I know that this is feasible. This is feasible because the right-hand sides are positive, and I also know it's optimal because this is unchanged, right? The coefficients here are unchanged, they're all non-negative. Okay, then you can find the new value. So the new max for the z. Okay, so the original problem is max, and then you put it in min and whatever. Okay, what would that be? We can use this formula. It will be z0. Let me write it. Z0 is 0 minus the CB. CB is the x4, x2, meaning take a -15, -4. So -15, -4, multiply by the B star, which we just computed, 3 and 16. 3 and 16. Okay, if you add up these numbers, and you will get 109. So you see, comparing to the old result, the original result, 106, we increased that value by 3 units. Is that right? So it's different, the maximum value. Okay? So is it clear how this is being carried out with one specific number? Now let's make it a bit more general. So, more general discussion. Okay, so instead of adding a specific number to the change, let's call this change a variable. Let's call it lambda. I add amount lambda onto B2, and I want to see how the answer responds to that. Okay, so change B2 into, so I will not write 53, I will say 50 plus a lambda. So I add some amount to it. Okay, so let's show what we do here. I will have a additional amount that I add on top. Okay, And then, of course, the solution will be different. It will respond to that. Okay. Okay, I mean, the setting is still the same, except now this B vector, I don't write it as this, I write it as my change, right? So I can still compute the B star, which will be B inverse times the B vector, which will be 28 and 50 plus lambda. Is that right? Okay, so the only change is I don't write 53. You can think I write 50 plus 3, and the 3 is the lambda. Okay, so I can break this vector into two vectors. One is the original one, and the other is the new piece that you add on. That is, you add lambda on the second element. Okay, and then you know this computation here, you actually don't have to do it. B inverse times the old B will be exactly the original right-hand side. So this one you can get from the tableau, the old final tableau. That will give you the number. So I will have 6, 4 plus, then you need to do B inverse times 0 lambda. B inverse is here. If you multiply this by 0 lambda, what you do is that you take the second row and multiply it with lambda. Is that right? First row is multiplied with 0, add on top doesn't do anything. So I get negative lambda for lambda. Is that clear? You carry this computation out. If you don't see it so quickly, you can just carry it out. It's not a big deal. So, okay, so I get this vector now. That will be the B if I make a change of lambda. And what do I need? I require this to be B star to be bigger than 0. So what does it mean? Well, each element will have to be bigger than 0. I'll have two inequalities. Is that right? And we can easily solve them. These are all linear constraints always. So lambda, the first one, lambda shall be less than 6. The second one is lambda bigger than negative 1. Is that right? So they both must be satisfied. So I know that lambda has to lie between negative 1 and 6. If it does that, then I know the old pivoting process can be used, and the right-hand side in the final tableau will remain non-negative. So that's what it says. So, so I can conclude if lambda is between that, then what will be the Z max? Well, then I can use this expression to compute my Z. Oh, okay. Z max or mean. It's negative Z mean. Okay, let's call it Z mean. I can use this expression to compute. So C0 is 0 minus, what is the CB? CB is negative 15, negative 4 times the B star, which is here, and I know it will be all positive already. So 6 minus lambda, 4 plus 4 lambda. That will be that. Okay, and you can get rid of the negative sign. There'll be plus plus, and you can do this multiplication and do this multiplication, add them up. You collect the constant terms, and you collect the lambda terms, and that gives you 106 plus lambda. So if lambda lies within this range from negative 1 to 6, then 1 unit of change in lambda is going to cause 1 unit of change in the optimal value. Is that right? Do you remember we talked about the coefficient in front of here? So this coefficient here in front of lambda, coefficient equals 1. We call that is the shadow price. That's the price you will pay if you make change on the right-hand side, all right? And we also made a connection that the shadow price actually comes from, or not comes from, it actually equals the solution of the dual. I want to make these connections. So for this original problem, how do we spot the solution of the dual in this tableau? If I form the dual problem, where would I find the optimal solution for the dual? On the coefficient in front of the slack variable. This will be the solution for the dual. Is that right? For the dual problem, that's the y1 optimal value, and this is the y2 optimal value. What we did here, we made a change in the second constraint, and meaning we made a change in that something is affecting from the second constraint. And you see, this one here is the shadow price for you make change there. And that's exactly the coefficient in front of this lambda. Is it okay? Just making these connections, all right? So that's the shadow price. Okay. Okay, so I would like to view it even from another point of view. So we see that if lambda remains in this interval, then the same pivoting process will end up with a positive b on the right-hand side, which means the left-hand side is unchanged. That means x4, x2 will remain the basic variables, right, in the optimal solution. And then and as long as that happens, I can compute in another way. So let's write this. So the final tableau will keep its shape. The left-hand side won't be changed, and you just need to modify the right-hand side. Okay. So which means the I should actually say the left-hand side in particular. The left-hand side of the final tableau is unchanged, meaning that all here will remain the same, meaning that these two numbers would not change, meaning that the solution, optimal solution for the dual, would not change. Okay? That's what I want to say. So, optimal solution for the dual is unchanged. Okay, so what do I have? It will be y star will be 2 and 1. Okay, and then you know if that has an optimal solution, it has a bounded optimal value. By duality theorem, the original problem takes the same optimal value. Is that right? So I can use that to find out the optimal value also. So let me put this up by duality. So this will give me the original value. So I can write the z min, whatever I'm finding here, will be the solution of the dual, the optimal value of the dual, which will be y star dot so the objective function is the 28 times y1 plus 50 plus lambda times y2. Is that right? That dot. So dot 28 and 50 plus lambda. Okay, and y star is just 2, 1. So if you put that in, you get 2 times 28 plus 1 times 50 plus lambda. And then what does that give me? Well, if you add this up, you will have 106 plus lambda. Of course, it has to be the same. You're just viewing the same thing from all different angles and recognize it. Okay, so we can go back maybe to the first example we had here, where we changed the B2 by 3 units. So for this example, lambda equals 3. Is that right? And by the general discussion here, I know 3 is on this interval between -1 and 6. Then the same pivot process can be carried out. The left-hand side won't be changed. And then this expression holds, meaning the change in the optimal value shall be 3. Is that what we have? What did we get there? 109, right? It's 106 plus 3. So it just verifies again this general observation. Is that okay? Is it okay, this discussion? So all these are in the favored case where the same pivoting process can be used. What if that is not the case? Then you need something else. So if now B star becomes negative for some elements, let's say I can easily do that. So here it says 6 units, right? Let's say I change B2 into 57. Just 1 unit too much. I change it by 7 units. And you can easily do this computation and find out the B star. Well, there will be the B inverse times now the right-hand side, and this will give you -1 and 32 on the right-hand side. So if you change that to 57, and you carry the same pivoting out, and you will get -1 here. And then the basic solution is not feasible. Is that right? You can have a basic solution, but it's not feasible, and it's totally useless. So what can we do in that situation? Okay. So we need something new, some algorithm to handle this situation. Okay. So that will be the next chapter we're getting into, 5-6. Okay, I'll put the name. The name actually gives away, but we'll come back to that. Here is a new algorithm called the dual simplex algorithm. Okay. So I want to say up front that this algorithm is a specific algorithm. Let's say right now I want to deal with this particular situation that I'm running into. Okay, let's say it's designed for that, and then we see it actually can be used in more general setting. So what situation am I in? I'm in a situation that the left-hand side is in this canonical form, and I have a set of basic variables, and the objective function has all positive coefficients. But the basic solution takes some negative value and is not feasible. How can I start from there and solve the problem? Is that clear? That's the point. Okay, so let me write down. What do we mean? This, in the end, is an algorithm to solve LP problems. In this particular, let me put it in the quotation sign. I call it canonical. It resembles very much a canonical form, but we could have some BIs negative. Okay? And we also would require all the CIs to be bigger than or equal to 0. Is that clear? So this is the starting point for this algorithm, and then we'll find a way of solving it. Okay, so what I want to do is explaining the procedure through an example, and hopefully it's all clear what we have to do, and we can summarize, or we just say it's clear. Okay, so I'll take an example. So look at a minimizing problem. Minimize z equals 10x1 plus 5x2 plus 4x3 subject to so fewer numbers. Okay, everything is positive. So this is a standard minimization problem, right? Okay. Okay, so the point of this example is to show that this starting point that we talked about here could also occur in other problems, that this algorithm could be useful in many other situations as well. Okay, and next class we'll see the application even in another problem. Okay, so let's say I want to solve this minimization problem, and it's not in the standard form, so I have to change it into standard form by adding slack variable. Let's do that. So add some slack variable, then I have the following. So I add x4 here and x5 here, so I'll have the constraints 3x1 plus 2x2 minus 3x3. Because it's bigger than 0, so I need to take away something, equals 3. So minus x4 is added there, 4x1, 2x3, and I need to subtract an x5 from the second equation. No, I copied the wrong number. So this is 10, it's not 0. So 10. So the second constraint is bigger than 10. Okay? I'll just write the constraints. All these are positive variables. Okay. So in order to use the simplex algorithm, we need this to be in this classical canonical form, meaning these two basic variables must have +1 as the coefficient in the front. Is that right? So here I have bigger than constraint. It ended up with a -1 sign in the front. So the old way that we have learned to deal with this will be adding artificial variables in the simplex algorithm. Then you add another one, x6, x7, and then you drive the sum of the artificial variable to 0. That's stage 1, and then you go to stage 2 to minimize. It's very irritating, isn't it? Especially here, you see that this is almost in canonical form. It just has a wrong sign. Wouldn't you prefer to, multiply this by -1, so this can be the basic variable, and then I deal with negative right-hand side. How about that? So let's do this. So I multiply by -1 everywhere. I have the following. If I write this down, I have -3, -1 minus 2x2 plus 3x3 plus x4 equals -3, -4 x1, 2x3 plus x5 equals -10. That becomes my constraint. And then I see that x4, x5 can be the basic variable, except that now the solution is not feasible. So let's observe basic solution for this problem, if I take x4, x5 as my basic variable, is 0, 0, 0, -3, -10 is not feasible. But do you see that the form here is exactly the form that I said this algorithm is going to start with from there to drive it to a solution, right? Okay, so here, now we go into this algorithm. So, okay, so what I will do will be, we will go through this algorithm and state it so we know for sure we understand how to use this algorithm, and then I'll give you some explanation why this works. All right? Is that okay? So let's set up the tableau. So -3, -2, 3, 1, 0, -3, -4, 0, -2, 0, 1, -10. Okay, that's what you put in, and 10, 5, 4, 0, 0, 0. Okay, and x4, x5 are the basic variables. Okay, so you put this in the tableau. So I will write on the right-hand side the thinking process. So what do you want to do? You see, if I use x4 and x5 as my basic variable, I ended up with a not feasible basic solution. So I still want to restrict myself into basic solutions. So my idea will be, I'm going to change my basic variable one at a time and go and visit all other neighboring basic solutions to find one that's feasible. Is that clear? It's kind of similar to the simplex algorithm. So, meaning I would like to switch one of the basic variable with some non-basic one here to see if it can make some of this positive. So this switching process is exactly the pivot process. That's exactly what it does, right? You perform one pivot, basically you change one basic variable into another, right? Okay, so that's the thinking process. Move to another basic solution by a pivot step. So in the hope that I will eventually end up in the feasible region. Okay, so then here comes the big question. Okay, so I realize I can just pivot. That's the same process we've been using. But the big question is, where do I pivot? Okay, so I will explain how to pivot, and then we'll explain the reason behind afterwards. So this pivoting process is in a way similar to the old one, but different. So in the old one, do we remember the old pivoting process? I would check which of these coefficient is negative, and then I select the most negative one. I choose a column first, right? After I have chosen a column, and then I look at the negative ones and check the ratio and choose the row. Here it's reversed, the order. I will pick a row first. So let's see, how do I find the pivoting row first? So any row can be used to pivot as long as it has negative b's. Those are the criteria. Okay, so any row with negative bi can be chosen. Okay, so here in this problem we can use either one, right? So b1 is negative 3 is less than 0, and B2 is negative 10 less than 0. So you can choose any of them. So let's say I make an arbitrary rule that I would choose the more negative one. It doesn't have to. You can choose the other one. It's just the same. Let's say I choose the more negative one. Say we choose B2. Okay, which means I would choose row K equals 2. Okay, once I found the column, now I need to find, I find the row. Now I need to find the column. Okay, so I have decided this is the row that I will pivot, and then I look at all these coefficients. So I see the 0 one for sure I can't pivot because it's not legal. You'll be divided by 0. So here I would look into the coefficients that are negative. Okay, I will consider only the negative ones. So I would choose among only among negative A to Ki, which are less than 0. So here I see that I have two candidates, negative 4 and negative 2. So which one should I use? Okay, so let's see. Here I actually have two candidates. A to 1 is negative 4, which I would choose, and A to 3 is negative 2. Okay. And then I have to make a decision between. So among them, what do? I will choose the one with the largest ratio. So the ratio now is made by taking the coefficient of the objective function in the corresponding column and divided by that A. Okay, so that will be the Ci over AKI. I compute all these ratios and I pick the largest one. So pay attention here. All these A's are negative that you choose as your candidate, and all those C's will have to be non-negative because the problem you set up. So the ratio will be negative. When you say you choose the largest one, you are choosing the one with the smaller absolute value. Is that clear? Okay, so let's see. So here in our case, what do we have? So the first one will be 10 over negative 4, which gives me negative 2.5. And the second one is 4 over negative 2, which gives me negative 2. Which one is bigger? This is bigger, right? It's smaller in absolute value. So that will be your pivoting point. Okay? You choose that as the pivoting point, meaning you replace x5 with x3 as a basic variable. So I will have x4 and x3 here. Okay? So let's say I carried out this pivot and I have the following table. Negative 9, negative 2, 0, 1. I get some fractions. Negative 18 and 2, 0, 1, 0, negative half, 5, and the last one is 2, 5, 0, 0, 2, negative 20. Okay. You see, by pivoting in this row, what I achieve is the right-hand side B in that position now is non-negative. Okay? We haven't explained why, but we observe it. Okay, now what do? Well, let's call this process P here. This this pivoting step here. Well, now I just have to repeat. As long as I have negative b's, I have to repeat this on all those negative ones. So now I see I have one more negative b. That's the first row, so I will pick the first row to pivot. So let's say I choose the first row to pivot. And then I need to choose which column, right? So I see I have two candidates, -9 and -2. Let me compute the ratio. For -9, I will get -2/9. That's the one. And then the other one will be -5/2. So which one is bigger? The first one is bigger, right? It's less negative, right? So you're going to pivot right here. Okay? And if you carry this out, I mean, you can easily do this in the LP Assistant. So if you carry this out, then I will be replacing x4 by x1 in the basic variable, and I have x3. So, okay, let me just write these numbers because just one step, then it finishes. 1/2, 0, -1/9, -1/6, 2 and 1, 0, -4/9, 1, 2/9, -1/6, 0. These are just numbers. -24. So I end up with this tableau where I see that now right-hand side are both positive, meaning this basic solution is now feasible, and all the C's are non-negative, meaning that's the optimal point, right? Is that clear? Sorry I went so low. Yeah, so now you conclude that's the optimal solution. Is that right? So let me write it here. Optimal solution. What was the original problem? Minimizing. So I can conclude Z min equals the negative of that is 24, obtained at, what is my basic solution? So x1 is 2, x1 is 2, x2 is 0, x3 is 1. So is it clear the procedure, how you should carry this out? Later I'll show you how to do this in LP Assistant. All you need to know is to find the position to pivot and you just click, okay? It will be not computationally intense.
So are we just pivoting the dual using the original? Are we just pivoting the dual using the original by doing this?
Carry out this process. Yeah. You can carry out this process in LP Assistant in a different mode. We'll show that.
Oh no, I'm just saying in general, what we're doing here. Are you essentially just pivoting the dual?
Yeah, that's what I'm coming into now. Now we have to explain why this works, right? Why this works. So is the algorithm clear? Do I need to write out a summary or is it clear? The book has a detailed summary of half page. Can I ask you to read that? Is it clear, the steps? So you basically set it in this form and then you repeat this pivoting process until you make all the B's positive, right? Non-negative. And then that ends the problem because those C's will remain non-negative. It will never get to negative. Okay. So let's try to explain why this happens. The problem is there. Okay, I can start from here, can I? I would like to have the tableau close to it. Okay, let me start from here. Let's try to explain why is this happening and why does this work? I mean, any reason this is working? Explanation of this algorithm, the dual simplex algorithm. Okay, so actually the name gives it away that it's actually solving the dual. Yeah, but let's see the connection. So what I plan to do will be just take this example, all right, and see the clear connection. And we don't do a general discussion here because we'll be convinced that it works, all right? So we have this original problem, which is written here, which is carried out by this algorithm in this tableau. And let's see, I set up the dual, I solve the dual, and see what I actually do there, okay? And then make all the connections. So set up the dual. So this is a minimization problem, and then the dual will be a maximizing problem, right? So I will be maximizing v, let's say, equals 3y1 plus 10y2. Are we all okay setting up the dual from this problem here? Change minimum into maximum. Get a y1, get a y2, and add them up vertically. Is that right? Okay. So that's the objective function. Subject to, if I set this up, what would I have? 3y1 plus 4y2 less than 10. 2y1 less than 5. Negative 3y1 plus 10y2 less than 4. They're all positive. I'm not writing it, but they're all that. So if we want to solve this, we have to put it in the standard form. We have to make it into a minimization problem. So I can rewrite. So you can put it into the initial point for the simplex algorithm. So rewrite into minimizing negative v, right? I can do that. Let me write it in the form that it's already good. So I add slack variables. So I have 3y1 plus 4y2, and I add a slack, y3 equals 10. 2y1, I add a slack, y4 equals 5. And 3y1 plus 10y2, I add a slack, y5 equals 4. And the objective function, I get negative 3y1 minus 10y2 equals 0 plus negative v. That's what I'm trying to minimize here. Question?
Should the last subject to equation be negative 3y1 plus 2y2?
Oh, yeah. Yeah. It's the 2 here, right? Yeah. Yeah, that's right. I copied over there. So it's 2 here. Sorry. I think I copied this in 10, this number. Thank you. Okay? So we see this is in canonical form. Is that right? y3, y4, y5, basic variables. And it's feasible. And we can put it into simplex algorithm and solve it. And let's try to solve this and see step by step what we are actually doing and connect to what we did over there. Okay? So I will set this up in a tableau and try to solve it. So okay. y1, y2, y3, y4, y5. y3, y4, y5. Okay, so let me put in the number. I will have 3, 4, 1, 0, 0, 2, 0, 0, 1, 0, negative 3, 2, 0, 0, 1, 10, 5, 4. -3, -10, 0, 0, 0, 0. So that's the initial tableau as I put in. So want to catch your attention. The A matrix, the part without the slack variable, you transpose it and make it all negative, and it's appearing here. Do we see that? If I transpose this and make everything negative, that's exactly that one. Okay, so I want to see the connection. Okay, so how do you pivot in this problem, the regular simplex algorithm? You check the coefficients to see if any of this is negative. And I find some negative ones. Let's say I pick the big negative guy. I will be picking this column with -10. Is that right? So that corresponds to my pick of -10 in this row. Then I will be looking at these 3 coefficients and checking which one I should pick. Okay? So I pick -10, I'll be looking at these 3 numbers. So in the regular process, what you do, you pick the 2 positive one, 2 and 4. And here it says, because it's all negative, so I pick the 2 negative one as my candidate, right? And then the regular simplex will say, I will be computing the ratio 10/4 and the ratio 4/2 to see which is smaller. Do we see that? So you will be doing the ratio is 10/4 and the ratio is 4/2, and you will choose which is smaller, and that is the one you will choose. Isn't that exactly the ratio we are computing? 10/-4, 4/-2, except it's all negative, and that's why you have to choose the large one. Do we see the connection? It's exactly what you're doing, right? So I say that's picked. Okay, so let's pivot that. I put on y2 for y5. I'll have y3, y4, and y2. Then let's copy the numbers. 9, 0, 1, 0, -2, and 2. 2, 0, 0, 1, 0, 5. And -3/2, 1, 0, 0, and half, and 2. And the objective function, -18, 0, 0, 0, 5, and 20. Okay, look at the tableau we got there and compare to the one we have here. So many similarities. 2, 5, 2, appearing 2, 5, 2. -18, 5, appearing -18, 5. They're so tightly connected to each other. Do we see that? And if you collect the non-basic variable, x1, x2, and x5, these 3 transpose, make a negative, is exactly y3, y4, y2. So y1 and y5. Okay, let's don't get into that. All right, so now what would you pivot normally here? You see I have a negative number. This column will be chosen. It's the same as I chose the row with -18, right? So I will be considering among these numbers, not this one, but among those 3. Is that right? Isn't that exactly these 3 numbers with a negative sign? It's exactly. And then here I would choose between 9 and 2, and I will compute the ratio 2/9, 5/2, and pick the small one, and that will be picked. And what did you do here? Well, you do the 2/-9, 5/-2, and you pick the big value, which will be the same, right? So that will be picked. All right, so this gives me the final tableau. You know that's going to end. So if I do that, I will get 1, 0, 1, 9, 0, -2, 9, 2/9, 0, 0, -2/9, 1, 4 over 9, 41 over 9, 0, 1, 1 over 6, 0, just numbers, 7 over 3, and I will have 0, 0, 2, 0, 1, and 24. Okay, so I see that now all of these are non-negative, then this is the optimal value for the dual problem. And by duality theorem, that should give you also the optimal value of the original one. You see they match. And also from the tableau of the duality problem, you will know that the optimal value for the original problem is hidden right here as the coefficient in front of the slack variables, right? Which is what we found here, 2, 0, 1. Okay? 2, 0, 1. So, is it clear? So what this dual simplex algorithm, what does it do by this kind of a pivoting process is actually exactly solving the dual problem. Are we convinced? Through this example? And then duality theorem will tell you that this will work. Yeah. Is that clear? Okay, now I will go into LP Assistant, and let's see how this can be carried out. All right. Okay, so I want to show you how to use LP Assistant to carry out this computation. Okay? So if you look at the algorithm that's being listed here, you see the pivoting process is the same. So if you click at the number, the LP Assistant will do the pivoting for you. That is still the same, but it's slightly different. The thing that is different is that okay, you have to still mentally choose which row you want to use. Once you chose a row in your head, then you will go and check the ratio, right? So when you compute the ratio, the old one will compute the ratio with B over that. And now it has to be those C over this. So that is the change in the algorithm, in the LP Assistant. It will help you automatically compute this ratio so you can choose the pivoting point. Is that clear? Okay, so we'll see how this can be done. The screen, the light. All right. Come on, select source, PC. All right. Okay, so that's the LP Assistant. I think, is it big enough? Can we see why there's a spotlight on the screen? Why is the spotlight on the screen? Can I front? Is it okay? I dim a bit so we can see more clearly. So, is it big enough? Yeah, I think that's okay. Okay, so let's put in. Let me show you step by step how, let's take this example that we had, and to see how one can do it in the LP Assistant. Okay, so the example we had on board. So we see we have 5 variables. I need to add another one and another one all the way to x5. And let's put in the numbers. -3, right? -2. 1, 0, 0, and the right hand side is -3. and negative 4, 0, negative 2, 1, negative 10, and 10, 5, 4, 0, 0, 0. Okay, I need to choose my basic variables, x4 and x5. So you set it up as normal in the edit mode, and then you go to the pivot mode. Question? Did I put something wrong?
Don't you get 1 under x4?
3, 2, oh, it's 3, right? I got it wrong. That's a 3?
Yeah. That's a 3 and a 1.
That's a 1. Yeah. Oh, I lost a 3. I typed a 1. Yeah. I don't know. I didn't hit 3. I skipped one number. Is it correct now? Oh, all right. So have you been wondering, under algorithm, there are two choices. One is the simplex, one is the dual simplex. For this problem, you have to switch it to the dual simplex. Is that clear? Okay. And once you have that, and then all you need to do is figure out where to pivot. So let me maybe move it a bit lower. Okay, so you have to first pick a row. Now I pick that one, negative 10. Then I need to choose between two negative numbers, negative 2 and negative 4. So you see, as you hover your cursor over negative 4, down there is a little number coming up, the ratio. It shows you the ratio between the C there and that A. Is that clear? So you can memorize that number, can we? What was that number? Negative 2.5 and negative 2. So which one has smaller absolute value? This one, right? So I click on that. Is that clear? So it's just click, click, but you have to know where to click, okay? And then I see that I still have a negative number, negative 18. I can choose between these two. These two are negative. So for negative 9, I get negative 0.2. For this, I get negative 2.5. So that's a bigger value, smaller absolute value. So I click on that. And it completes the computation, because now this is positive. All of these are positive, and all of these are also positive, non-negative. And then that's the solution. So is it clear how to use the dual simplex? Any questions? Is it okay? Any questions? Last chance? All right. So there will be homework problems for you to play with this dual simplex and get familiar with that. All right. I'll turn back on the light. Okay, so this is one application of using this dual simplex method. And actually, okay, so there are still many questions remain. Say if you have a random standard problem, can you always drive it into this form that we can start this dual? That is unanswered. And why this process really work? All we did was through this example and see the close relation with the solution for the dual problem, right? If you want to have a rigorous proof, there will be more details to fill in, okay? But we're not going to do that. I'll just make these comments. And the problem and the algorithm can actually be a little bit more general. So next class, we'll look at a situation where you have a system of LP you solved, and then some new constraints come. You might need to add one new equation for the constraint or two new equations taking different form. How does it affect the solution? And then you will see this dual simplex method will be very useful in that setting, right? Okay. Okay, I'm not going to start that chapter. I will save it for next week. Any questions? All right, then we finished.